Ladies and gentlemen, I'm honored to have opportunity to present work of my colleagues and mine entitled 5 Generations of High-Order Basis, General Approach for Highly Accurate and Efficient EM Modeling. I'm Branko Kolundzija, Professor at School of Electrical Engineering at University of Belgrade, founder and chief architect of WIPL-D company and software. The research and development of methods for solving electromagnetic field problems arose with the advent of first computers. The first commercial software package were launched in early 90s. Very soon, these tools become indispensable in the design of antennas and related structures. Nowadays, it is considered that 3D simulation algorithms and software attained their mature phase. However, commercial software is still far away from fully satisfying the ever-growing needs of academia and industry. There are increasing demands for more accurate and faster simulation, of more complex and larger scenario, from very low to very high frequencies, and dealing with materials of very low to very high contrast. Hence, there is a constant need for new generations of EM simulation tools. One of the most powerful methods for 3D modeling in frequency domain is based on method of moment solution of surface integral equations. This presentation will cover 5 generations of such method as developed by Micro Group at University of Belgrade and WIPL-D company. In late 60s, Professor Jovan Surutka, Branko Popović, and Momčilo Dragović initiated the research and development of methods for analysis of thin wire antennas. Modest computer resources motivated researchers to devise advanced methods capable of solving problems using reduced resources. One possibility to reduce the resources was to use polynomial approximation of current along thin symmetrical cylindrical dipoles, as published by Professor Branko Popović in Proceeding of IEEE. As a student, I had a chance to work with Professor Antonije Đorđević on the analysis of rectangular scatters, which was presented at Serbian conference ETAN. At that time, I had a dream to extend the analysis of a single plate to analysis of composite structures made of 2 to 3 wires and 2 to 3 plates. Nowadays, we can solve problems of thousands of wires, metallic and dielectric patches at a desktop PC. Although the power of MOM-SIE algorithms has been more or less continuously enhanced, we can distinguish 4 phases or generations of this development. For each of these generations, as well as for future ones, we always begin with the same initial question: how to develop effective MOM-SIE method? There are 2 basic steps in development of effective MOM-SIE method. In the first step, we choose surface integral equation to be solved, a form of basis functions, and the type of test procedure. In the second step, 2 most demanding tasks are to evaluate the impedance integrals and solve the matrix equation. At an early stage of MOM-SIE development, we choose EFIE and PMCH-WT as surface integral equation, high-order basis function of polynomial type as basis functions, and Galerkin method as test procedure. Later, the choice of test procedure has never been questioned. Experience of other authors is practically the same as ours, as shown in the example. The graph shows relative error in percents of half-wave dipole antenna versus order of current expansion for various test procedures. It is seen that Galerkin testing provides faster convergence of results than other test procedures. The choice of surface integral equation has been re-examined from time to time, but has never been changed. The reason for that will be explained in the next slides. Choice of basis functions and their implementation was most dynamic part of development of MOM-SIE, and it will be the major topic of the rest of presentation. In EFIE, the unknown currents induced over metallic surfaces are determined from the boundary condition that tangential component of electric field is zero. In PMCHWT, a multi-region problem is decomposed into single-region problems, coupled by unknown equivalent electric and magnetic currents. The unknown currents are found from condition that tangential components of electric and magnetic fields are equal from both sides of boundary surfaces. Why we did choose EFIE and PMCHWT? These equations are the only surface integral equations that do not require knowledge of outward normal at boundary surface. They're also the only surface integral equations that fully satisfy the power balance if solved by the Galerti method. Namely, the total power delivered to antenna bivoltage generators is equal to the sum of the power dissipated in the antenna and the radiated power. In addition, EFIE is the only surface integral equation that enables thin plate and thin wire approximation. In the first case, shown left, the plate of thin thickness can be replaced by infinitesimally thin plate if its thickness is much smaller than the wavelength. In that way, the number of unknowns needed for EM modeling is halved. In the second case, shown right, the plate model of wire can be replaced by single segment model if the wire radius is much smaller than the wavelength. That way, the number of unknowns needed for EM modeling is reduced around 10 times. Higher order bases extend the limits of EFIE and PMCHWT. Generally, EFIE suffers from spurious resonances. Higher order basis suppresses the spurious resonances, as shown left. By increasing the number of unknowns, the width of spurious peak in RCS response decreases. This decrease is much faster if high order bases are used. In particular, the results for order 3 are not shown since the peak is significantly narrowed and becomes hardly visible. If a dielectric cube made of material having the same properties as surrounding air is illuminated by a plane wave, theoretically there is no scattered field. If such problem is numerically modeled using PMCHWT and the equivalent currents are not exactly determined, the approximate scattered field is not equal to zero, as shown right. Again, such field is suppressed by increasing the number of unknowns, and in particular, by increasing the expansion orders of high-order bases. Owing to high-order bases, the RCS of dielectric cube can be suppressed compared with that of PEC cube for 60 dB in single precision and 120 dB in double precision. Choice of basis functions consists of two steps: definition of building elements used to model the geometry of the structure, and approximation of currents along the building elements. The flexibility of geometrical modeling we based on two types of building elements: right truncated cones for metallic wires and bilinear surfaces for metallic and dielectric boundaries, as shown in two pictures left. Bilinear surface is a quadrilateral patch defined by 4 nodes arbitrarily placed in the space. Using these building elements, the geometrical models of antenna tower and car shell are obtained as shown in two pictures right. Figure in the left upper corner illustrates higher order bases along the chain of 4 wire segments. Expansion of the first order consists only of doublets, also known as triangle basis functions in method of moment-based thin wire analysis. This low-order expansion actually enables piecewise linear approximation of currents. Accuracy of the approximation can be increased in two ways. The first way is to subdivide wire segments into subsegments and increase the number of doublets accordingly. This way is known as H refinement. The second way is to add singlets. Singlets are bases of order higher than 1 equal to 0 at the segment ends. This way is known as P refinement. Advantage of high-order expansion over the low-order expansion is shown on the example of thin wire scatter 10.5 wavelength long. Relative root mean square error of the current distribution is shown versus total number of unknowns for various expansion orders applied to each subsegment. It is seen that by increasing the expansion order while retaining the same total number of unknowns, relative error quickly decreases. Generally, it is found that for electrically longer wires, the low-order approximation requires 10 unknowns per wavelength, while higher-order approximation needs only 4. Low-order approximation over plates consists of rooftop bases. Higher-order approximation is obtained by adding singlets of higher order. It is seen on the example of square scatter, 1 wavelength long, that higher-order basis results in much finer approximation of both current components when compared with that of low-order approximation. Usage of higher-order basis requires automatic setting of expansion orders n. N equal to 1 corresponds to low-order approximation by rooftop basis functions. This order can be used up to the maximum patch size of 1/6 of wavelength. By increasing the expansion order for 1, the maximum patch size increases by 1/3 of wavelength, as shown in the table. In order to estimate efficiency of higher order basis, let us consider square patch of average electrical size for expansion orders n going from 1 to 7. The corresponding numbers of unknowns per patch and per wavelength squared are given in the table. It is seen that number of unknowns per wavelength squared can be reduced for 1 order of magnitude if high order bases are used instead of low order ones. Implementation of higher order bases requires specific adjusting for wire-to-plate junctions, protrusion of wires through dielectric surfaces, composite dielectric junctions, and electrically large plates. Let me elaborate only the last case in more details. If electrical length of patch edges exceeds the given maximum patch size, the patch is automatically subdivided into minimum number of patches that satisfy this condition. To demonstrate the robustness of high-order bases, consider example of standard 20 dB horn antenna. H-plane radiation pattern is obtained using 10 sets of current expansions resulting from various values of maximum patch size. Negligible numerical noise can be observed at level of -40 dB below the main lobe. Simulations based on first generation of high-order bases have been performed on single-core 32-bit CPUs with 2 GB RAM limit, which could store complex matrix of maximally 15,000 unknowns. Since high-order bases need about 30 unknowns per lambda squared, the size of solvable problems was limited to surface area of 500 lambda squared for metallic bodies. Advent of multi-core 64-bit CPUs brought the new possibilities: parallelization of calculations and storage of matrices of practically unlimited size. In the first step, parallelization was applied for the matrix solve, and matrix fill became bottleneck of 3DM simulation. In the second step, new algorithms were developed to enable parallelization of matrix fill, so the size of the solvable problems increased up to 100,000 unknowns. However, the available RAM was not sufficient to store such great matrices, while there was enough space at hard disks. Hence, in the third step, out-of-core matrix solver was developed, and matrix fill adjusted accordingly. Thus, for the largest problem, the matrix solve again became a bottleneck. Adjusting of GPU cards for parallel computing opened the possibilities for massive parallelization and much faster simulation. However, available libraries for GPU matrix solve enable only in-core GPU operation using VRAM that is usually much smaller than CPU RAM. Hence, in the first step of GPU parallelization, an out-of-core GPU solver was developed, enabling the usage of full CPU RAM for matrix store. In the second step, the functionality was enhanced so that matrix could be fully stored on hard disks. In the third step, the functionality was further enhanced so that more than one GPUs could be used in parallel. Thus, solution of 100,000 unknowns is enabled in a few minutes at multi-core CPU PC equipped by GPUs. Finally, a CPU-GPU cluster solution was developed. In what follows, efficiency of high-order basis combined with CPU-GPU cluster parallelization will be demonstrated. Graph on left side shows acceleration of matrix fill versus number of unknowns when number of threads is increased from 4 to 48. Graph on the right side shows acceleration of matrix inversion versus number of unknowns when 4 GPU cards are used instead of 48 CPU threads. Antenna placement on F-16 fighter is analyzed at frequency of 2.5 GHz. Electrical length of the model is around 125 wavelengths. Number of unknowns used in simulation is around 140,000. PC used for simulation has 48 CPU hyperthreads and 4 GPU cards. Total simulation time is 19.5 minutes. Matrix solve time is 9.1 minutes. Cassegrain antenna is analyzed at frequency of 25.5 GHz. Dish diameter is 2.9 meters, which corresponds to 246 wavelengths at operating frequency. Number of unknowns used in simulation is around 160,000. Total simulation time is 44.1 minutes. Matrix solve time is 17.1 minutes. Tank T32 is analyzed at operating frequency of 3.6 GHz. Monostatic RCS is determined in 70 directions. Number of unknowns used in a simulation is around 800,000. The problem is solved using out-of-core simulation. PC used for simulation has 96 hyperthreads and 10 GPU cards. Total simulation time is 14.5 hours. Matrix solve time is 10.1 hour. Monostatic RCS from Global Hawk is determined at operating frequency of 5 GHz. Maximum dimension of aircraft is 36 meters, which corresponds to 600 wavelengths at operating frequency. RCS is calculated in 1,801 directions. Number of anodes used in simulation is around 550,000. Simulation is performed at cluster having 8 nodes, each with 2 GPU cards. Total simulation time is 16.2 hours. Efficiency of parallelization is around 80%. Second generation of high-order basis enabled solution of electrically very large and complex problems. However, in some cases, we observed the problems with stability and convergence of the results. These problems are resolved and new limits are achieved by using 2 methods. The first method is advanced matrix equilibration to balance source and field quantities in surface integral equations and basis and test functions in method of moment solution. The second method combines singularity extraction technique and singularity cancellation technique to achieve highly accurate evaluation of method of moment matrix elements. Extended limit for low contrast materials is demonstrated on the example of dielectric sphere of 1 wavelength in diameter, illuminated by theta polarized plane wave. V-static RCS in XOY plane is shown for relative permittivity, decreasing from 1.3 down to 1 plus 3 multiplied by 10 to the minus 6. The results are compared with that of sphere filled by vacuum. A relative difference in permittivity with respect to vacuum, delta E, can be distinguished down to 10 to the minus 6. Extended limit for high contrast material is demonstrated on the example of conducting sphere of 1 meter in diameter, illuminated by theta polarized plane wave, which is analyzed at frequency of 300 MHz. Electric near field is shown along y-axis for relative permittivity, increasing from 1.3 up to 1 plus 3 multiplied by 10 to the 6. Dynamic range of results is 900 dB. A relative difference in permittivity and permeability with respect to vacuum can be distinguished up to 10 to the 6. Extended limit for characterization of shielding effect is demonstrated on the example of conducting spherical shell illuminated by theta polarized plane wave. Outer radius of the shell is 1 meter. Shell thickness is 5 centimeters. Analysis frequency is 3 MHz. Figures show near field along z-axis in dB micro and picovolt over meter. Results obtained by MIA series and those obtained by simulation are in good agreement. Shielding efficiency of 200 dB is accurately characterized. Extended limit for low frequency breakdown is demonstrated on the example of perfect electrically conducting sphere and dielectric sphere, both of 1 meter in radius, illuminated by a plane wave. Relative permittivity of the dielectric is 4. Monostatic RCS is shown in the frequency range from 1 Hz to 100 MHz. Results are stable down to 10 Hz. Ability to effectively model electrically large structure with small details is demonstrated on measurement setup scenario of a PCB antenna. Simulation is performed in frequency range from 2 MHz to 2 GHz. Simulation and measurements are in good agreement. Maximum dimension of setup is 0.77 meters. Radius of thin coaxial line is 0.164 millimeters. Maximum size of scenario is greater than 5 lambda. Minimum size of details is smaller than 1/1,000,000th part of the wavelength. Using advanced techniques, the impedance integrals can be evaluated with prescribed accuracy, nearly to machine precision. Let us consider biconical antenna as shown in insets of the figures. Relative root mean square error of method of moment matrix versus prescribed number of significant digits is shown in the upper picture for various expansion orders. Relative error of input impedance is shown in the lower picture with respect to reference value obtained for 15 significant digits. It is seen that by increasing the expansion order, the number of significant digits of solution quickly decreases. Maximal usable order in single precision is 12. Maximal usable order in double precision is 20. However, in the case of arbitrary composite metallic and dielectric structures, the maximal usable orders are 8 and 12 respectively. These limits can be overcome if high-order bases are maximally orthogonalized. Maximally orthogonalized bases are derived starting from classical hierarchical polynomial bases. As shown right, two-step Gram-Schmidt procedure is applied to mutually orthogonalize these bases. Thus, max-ortho singlets are obtained as shown down, and max-ortho half-doublets are obtained as shown down right. Conditioning of the matrices obtained by classic and max-ortho bases is demonstrated on the example of trihedral corner reflector. The reflector is illuminated by a circularly polarized plane wave. 3D graph of bistatic RCS is shown left. Condition numbers versus expansion order are shown left down for classic basis and right down for max-ortho basis. By increasing the expansion order, the condition number increases quickly for classic basis, while it stays practically constant for max-ortho basis. Special care was devoted to implementation of max-ortho basis. Using recurrent formulas for max-ortho basis and Legendre polynomials, the impedance integrals are obtained with prescribed number of significant digits. High-precision integration enables usage of max-ortho basis of ultra-high order, as demonstrated on the following examples. In the case of biconical antenna, relative root mean square error of matrix elements versus number of significant digits for varying expansion orders is shown left. In the case of thick dipole antenna, a relative root mean square error of current distribution versus number of unknowns for various expansion orders is shown right. In the case of axially symmetrical antennas, the expansion orders up to 128 can be effectively used. Extended limits of peer refinement are demonstrated on RCS results obtained for a 100 lambda long airplane. Initial minimum and maximum edge lengths are 0.5 wavelengths and 25 wavelengths. Model is remeshed to minimal number of patches, whose maximum patch size is not larger than k wavelengths, where k goes from 2 to 10. Initial results, shown on the left and in the middle, are obtained using automatic setting for expansion orders. Additional results, shown on the right, are obtained by p-refinement, increasing expansion orders by 1. Consider the part of radiation pattern given on the left and circled in red. Enlarged view, given in the middle, shows the numerical noise of 10 dB, caused by usage of various max patch sizes. P-refinement reduces this numerical noise to 2 dB, as shown in enlarged view on the right. How high we can go with expansion orders in the case of metallic plates. Consider square plate scatter 10 wavelengths long with broadside incidence. Instead of using 10,000 patches with rooftop bases, we can use single patch of ultra-high order bases of order 31. Its current distribution is shown on the left. Consider next square plate scatter 20 wavelengths long with oblique incidence. Instead of using 40,000 patches with rooftop bases, we can use single patch of ultra-high order bases of order 61. Its current distribution is shown on the right. In order to fully exploit power of high-order bases, it is very important to have optimal P and H refinement performed in adaptive and automated way. Currently, we are working on options that should provide such performance: refined edging, automated imaging, and P-refinement of patches based on their shape quality factor. An example of refined edging is shown in the picture. Power of high-order bases cannot be fully exploited if curved surfaces are modeled with bilinear surfaces. Hence, we are working on EM modeling that includes biquadratic and bicubic patches. Potentials of such modeling are demonstrated on canonical example of metallic sphere of 6 lambda diameter. The sphere is modeled by 24 bicubic spline patches. Simulation is performed using expansion order 9. Approximate current distribution shows very smooth transition of currents at junctions of patches, as shown right down. P-refinement of polynomial expansion is relatively inefficient when accuracy of local singular effects need to be refined. This goal can be easily achieved by adding singular basis functions, as can be seen from figure right down. However, in general case, implementation of high-order basis augmented by singular basis is a difficult task, and we are still exploring how to do that. 5 generations of high-order basis are summarized in this conclusion for those who like to read. With this, I conclude my presentation. Thank you.